Today we're going to discuss how small language models and quantization are going to heavily impact the way we build agentic systems, and even the way we look at AI in general. My name is David Von Thenen, and I'm an AI ML engineer. I initially got my start in the AI space doing NLP related projects, so that's natural language processing. But I have a wide variety of interests including AI on edge, vision, and even creating medical models to detect debilitating diseases. I previously came from the Kubernetes and CNCF ecosystems, and prior to that I was in the backup recovery solution space working on distributed large-scale backup for VMware vSphere. For the agenda today, we're going to start by talking about some of the unsettling trends in AI. We're going to do a review of recent history, and we're going to use that context to frame our discussion here today. Next, we're going to discuss what small language models are, and more importantly, the economics behind using them. Then we're going to talk about fine-tuning and quantization, and why that's important for small language models. Finally, we'll end with using small language models as a foundation for building out agentic AI solutions. We'll wrap everything up with a demo leveraging our mixture of experts architecture. So let's start with some observations of what's happening in the AI space. We're going to start with a review of recent history and use this to frame our conversation. By this point, the entire world has heard about OpenClaw. But for those that aren't familiar, OpenClaw is a completely autonomous agent that crafts a plan on how to tackle a problem and then executes said plan without human intervention. OpenClaw is the fastest growing open source project ever, and it did so in a very short period of time. It has far surpassed other open source projects like the Linux operating system itself. If we're just using GitHub stars as the metric, at the time of presenting this, OpenClaw is currently at 359,000 stars on GitHub. I think the project in itself is pretty amazing for what it provides, but for me, this wasn't the big takeaway from the explosion in popularity. For me, the news that followed afterwards was the real story. There were in fact two parts to the story. The first was the security issues that OpenClaw faced. It had very little in the way of protecting itself against attacks from prompt injections and other various forms of intrusion. The second story that came out was the amount of money being thrown at API or token costs to have this autonomous agent to work and act independently. I've included a couple of news clippings here, but one such incident reportedly burned $2,200 overnight in a 12-hour period. But to me, this was the real story. The amount of money that we're burning on tokens currently, but more importantly, what that might look like going forward. So let's go back to around the time of NVIDIA GTC. NVIDIA CEO Jensen Huang made the statement that if your top engineers aren't burning at least $250,000 in tokens, then there's something wrong. You might be thinking, this sounds super hand-wavy and fictitious. I think Jensen Huang might actually be foreshadowing things to come. In the second picture, we have a Twitter post where Uber gave 5,000 engineers access to Claude Code in December, and by April, they had burned through the entire token budget for the year. So we're talking serious amounts of cash just to run inference on these AI systems. This news article hit several months before NVIDIA GTC, but I think it puts a good lens on the discussion today. NVIDIA made a deal with Grok for the tune of $20 billion for a non-exclusive agreement for their Tensor Processing Unit or TPU technology. For those that aren't familiar with Grok, they're an inference platform where they not only provide inference as a service, but they also manufacture and build their own power-efficient hardware to support their platform. The founder of Grok was actually the person who led the TPU effort at Google. As we move forward today in this session, I want you to keep the information from these three slides in the back of your mind. So let's jump into the core of our discussion here and talk about small language models and their economics. What is a small language model? Well, a small language model is actually very similar process-wise to a large language model. Language models process text input, understand context, and generate natural language content or output. You ask a question and it generates an answer based on the context of that particular question. Small language models are a subset of models that require fewer resources to run. Instead of trying to know everything there is to know, small language models focus on targeted areas of knowledge. A significant number of small language models only focus on basic language understanding itself, whether it's English or a language of your choice. You can run these small language models on modest or inexpensive GPUs and quite possibly even CPUs. At the end of the day, the intent of using small language models is for faster inference, and it requires fewer resources, which cuts down on infrastructure costs like power, cooling, and water. For things that small language models don't have in their knowledge base, you can teach them new behaviors and information, which we'll discuss in the next section. Here's a slide showing about the economics or token cost differences between small and large language models in a more in-depth study. In this chart, you can see the breakdown between higher complexity problems versus lower complexity ones. If you're comparing the difference between fine-tuned small language models and large language models tackling high complexity problems, you're looking at roughly 94 times increase in the monthly cost using an LLM. When you compare small language models and large language models tackling lower complexity problems, an apples to apples comparison says you're looking at roughly a 100 times cost difference for inference. So putting aside market fluctuations and current pricing, you're looking at roughly 100 times lower cost for inference using these small language models. Those are pretty significant numbers. Previously, everyone was looking at large language models as smarter means bigger and more is better. But with the reality of what's happening today, that's going to cost you a lot potentially. Even $2,200 in a 12-hour period a lot, and that doesn't make a lot of sense. The takeaway in this session is to select the right model based on the complexity of the question being asked. You don't need to throw the most powerful model at something when you're doing something as simple as summarization, for example. What the graphic here is showing you is if you actually look at the complexity assessment of what most prompts are being provided to language models, 80% of them are just routine queries or prompts, where it just might need a small language model or a model fine-tuned with RAG to provide a great answer. 15% fall in the very complex reasoning bucket. This is where you might need a wide variety of skills touching on many subjects, which is better suited for an LLM. And 5% of the queries are so complex you might need a human in the loop to intervene to provide more information to your AI solution. Let's read between the lines for a second. This slide is the foundation for why you're starting to see the rise of services like OpenRouter, which its primary value is to dynamically make decisions on which API to select for inference in an effort to lower inference costs. And if you're still not convinced how important small language models are, here's a research paper found on Archive from the NVIDIA research team with the title, "Small Language Models Are the Future of Agentic AI." Why is this important? Well, it's important for two reasons. The first, NVIDIA's core business model is more and faster GPUs. Their entire well-being for the most part is attached to how many GPUs they sell. The more waste in terms of oversizing your language model, the more money they're making because they need to sell you more GPUs. Second, they understand even from a credibility standpoint that engineering the correct solution and right-sizing the language model is extremely important when you're building out an AI solution. They understand what's coming on the horizon and saying the obvious thing, that small language models or architectures using a mixture of experts are the future of agentic AI. So now that we've talked about why small language models are important, let's talk about the force multipliers we can use to make small language models compete in our AI tasks. So we're going to talk about fine-tuning and quantization. So what is fine-tuning? Fine-tuning is the process of imparting knowledge directly into the weights of an existing language model. First, you start off with an off-the-shelf pre-trained model. These models tend to focus on basic language, and some have already been focused for a particular type of task. Then you have training data, which is used to specialize that model for one specific type of job. What you're effectively doing is you're creating a subject matter expert. You're imparting more data and information into the weights of that particular model, and updating its vocabulary so the model is better able to answer questions in that new subject or domain. But at the end of the day, what you're ultimately trying to do is change the behavior of your model. So a non-data sciencey way to think about it, the analogy I like to use is fork a given project on GitHub, create a feature branch that massively changes the purpose of the particular project, but is geared towards one purpose. That's fine-tuning. I wanted to briefly talk about the difference between fine-tuning and RAG. More importantly, why you might need to use both in your AI solution. For review, what does RAG or Retrieval Augmented Generation do for us? The idea of RAG is we're supplementing our language model by providing it data or information that it has not been trained on. So the way I like to think about it is you're supplying information along with the user's question, and you're effectively saying, take this into consideration when you're creating your answer. So how is that different from fine-tuning? Fine-tuning is the process of changing the behavior of a model and specializing it for a specific purpose. For example, if you ask a model a question on a particular domain where that model hasn't been trained on, say a medical domain, That model won't know how to digest the problem because it doesn't understand the vocabulary and concepts within that domain. Fine-tuning is imparting this new knowledge and understanding via concept associations from datasets into small language models' weights. That's the difference. Why might you need to do both? Fine-tune a model and supplement it with RAG data? You fine-tune a model so that the model understands the problem domain itself, and you also might need to use supplemental data that model has not been trained on because there is newer information available. After you fine-tune the model and create a subject matter expert, you optionally have the ability to quantize the model. So what does quantization do? It allows us to use simpler mathematical representation within the model to make the computational aspects of the model more conducive to a budget GPU or CPU's mathematical capabilities. By changing the numeric representation, it translates to smaller byte requirements to load the model into memory and changes the computational resources required. Because you're making the math easier for a GPU or CPU, the inference speed is faster and the GPU or CPU memory requirements are a lot lower. This is a good before and after graphical representation for quantizing a model. Before quantization, you have a higher memory footprint. You have higher processing power where you might need to have a GPU. The inference speed is lower because you're dealing with a larger model trained on a larger data set. But the correctness is very, very high because of all that training data. Again, the reason why you're picking this type of solution is because you have a GPU to assist with all the computational processing to get an answer with the highest reasoning available with a massive knowledge base. After quantization, you're decreasing the memory footprint required. You're decreasing the processing power, as in you might not need a GPU. The inference speed is increasing because we're reducing non-relevant knowledge, but the correctness is going to take a very small hit because the model is no longer a general purpose, I know everything model. It should be noted that quantization can in fact help memory and inference speed even if you're using a GPU. For example, NVIDIA has a number of preferred formats. The most common is BF16, which is a different representation for a floating point 16 number. There are even more formats emerging, like NVFP4 and MXFP8. Quantizing using one of these formats can give you a dramatic boost in inference performance even on an NVIDIA GPU. There are other compute accelerators out there, even for CPUs. Intel has the AMX extensions, which is the advanced matrix extensions. Apple has the MPS, or their neural engine acceleration, which uses the MLX library to decrease memory consumption and increase inference speed based on its supported numerical operations. Google has been building their own hardware for training and inference for years. Their focus has been on power efficiency in AI and ML applications because they need to run things at massive scale. Remember that NVIDIA licensing agreement with Grok? Even NVIDIA wants to get in on the power efficiency game. If you remember the flutter of news stories around OpenClaw, there was this massive amount of hype, well justified might I add, around purchasing Mac minis. In fact, Apple was selling out of their minis. The question is, why? People want to run OpenClaw on Apple Silicon because of its neural engine acceleration, to run inference on local models for free, as in $0 cost for tokens. Now, let's get into the crux of our presentation here, using small language models with agentic systems. So what is the definition of an agentic system? An agentic AI typically has the following attributes. It has some form of memory so that it can remember what it's planned out and what tasks it's already completed. They autonomously decide what tasks they need to do in order to accomplish their goal. Likewise, they independently define what done looks like. At a high level, this is how OpenClaw functions today. In practice, you have at least one language model. You have state and memory to access data or information. You have an agentic loop which causes you to collect more information or refine the process and answer. So in terms of implementation in different architectures for an agentic system, there are many different ways to define what the agentic loop looks like. Some examples. The simplest is the Ralph loop. Then you have React, or reason then act. There's planner executor, and also multi-agent. This isn't a complete list, and we don't have the time to talk about all of these, but we're going to focus on one, the multi-agent architecture, for today's conversation. In our demo, we're going to leverage the orchestrator architecture. The orchestrator pattern utilizes multiple agents to answer problems and is the most sophisticated amongst the different architectures. There's usually a single agent that acts like a conductor to coordinate attacking a problem and enlisting our other agents or tools in answering questions. Each agent has their own specific expertise and capability, hence the name mixture of experts. This architecture often performs better, providing more accurate results or outcomes when compared to a single agent or LLMs on a loop. But it comes at the cost of more coordination overhead, and debugging becomes challenging because now you're dealing with a distributed system. We're going to leverage agent-to-agent protocol in our multi-agent or mixture of experts architecture. For those that aren't familiar with agent-to-agent protocol, it's a protocol or contract on how agents talk to each other. It supports streaming HTTPS, JSON RPC, and support for gRPC was officially added in the 0.3 release. This project was initially created by Google, but has since been donated to the Linux Foundation. You can find more information using the links on this slide. Agent-to-agent is what allows agents to communicate in a decoupled and distributed environment. This is the high-level architecture diagram for our demo. We're going to build an agentic coder which leverages a SQL expert and a Python coding expert. I've built these two agents by fine-tuning and using Qwen 2.57 billion parameter model, and then quantizing the models for efficiency. Then we're going to use a coordinating agent to coordinate the workflow between these two agents. For our coordinating agent, we're going to use a model specialized for this exact function that comes from NVIDIA. It's called Nemotron Orchestrator. If you're not familiar with Nemotron Orchestrator, its purpose is to orchestrate workflows efficiently. It coordinates multi-turn agentic tasks between any number of agents using a wide variety of mixture of experts. I've attached a research paper that's available on Hugging Face, which discusses the performance of this model compared to others like OpenAI and Anthropic, using benchmarks like Humanity's Last Exam. What's really cool about the Nemotron Orchestrator model is that it's a small language model that you can run locally on a laptop, all while performing better than some of these more expensive models. Again, we are lowering the infrastructure and inference costs without compromising the quality of the answers. Let's jump into our demo for building an agentic coder solution. So for our final demo, we're going to build an agentic coder using the Python and SQL fine-tuned and quantized model. This is what the architecture for our agentic system is going to look like. We're going to use agent-to-agent protocol in order for the agents to talk to each other, and there are three of them. One is taking the fine-tuned Qwen model that now understands Python, putting an agent-to-agent protocol wrapper around it so that it is a Python subject matter expert. Our second agent is our SQL agent, again using our fine-tuned Qwen 2.57 billion parameter model that now understands SQL. And since this is a multi-agent agentic architecture, we're going to enlist the help of a coordinating agent, and that is that Nemotron Orchestrator 8 billion parameter model. This orchestration agent is going to coordinate all of the activity between the Python agent and the SQL agent in order to provide an answer to our given question. So we're going to give our agentic system a coding problem that is going to require both SQL and Python knowledge. And this is the task that we're going to give it. Write a simple Python main-style application that queries a SQLite 3 database to return the employee who has the highest salary. And you can see our default schema for our employees table right here. So the first thing we need to do is we need to start our Python and our SQL service. And because we're running our fine-tuned quantized model, which is suitable for our MacBook that I'm running here for the demo, we're going to run Python service mlx.py. So this is the fine-tuned and quantized model suitable for Mac Silicon to take advantage of the neural processor on my MacBook. So let's go ahead and start that service. Next, we're going to start our SQL service, which has a agent-to-agent wrapper so that we can ask SQL-related questions. Finally, we're going to start our orchestrator agent. This is what's going to coordinate the activity between our SQL agent and our Python agent. And I'm just going to run our service in CLI mode, which effectively just kicks off the query. Again, our problem is we have a given table of employees. We want to create a Python application that returns the highest paid employee. So let's go ahead and run our orchestrator service using Nemotron orchestrator 8 billion parameters. So as you can see here, it's taking the problem and it's now reasoning through what things it needs in order to answer the particular question. And so you're seeing in real time the steps, the thinking steps that are required in order to solve this problem. And as you can see here, it already knows to enlist the help of the SQL agent in order to bite off the SQL portion of our problem. Next, you can see that it's returned, and it now knows that it has the SQL statement in order to figure out what the highest paid employee is. Now it realizes that we need to create a Python code using the Python agent in order to take that SQL statement and call it from Python. So here you can see that it's using the agent-to-agent protocol to enlist the help of our Python agent. So this is taking the SQL statement, which you can see right here, and providing that information to our Python agent in order to write Python code to make that SQL call. And as you can see here, we have our final answer. We have the SQL statement, which is just for our information that is used, and here's the Python code to query the employee's database using our SQL statement in order to print the result of the highest paid employee. So what the most important thing to note here is we're running 3 different language models. We're using a fine-tuned SQL model, small language model. We're using a fine-tuned Python small language model. And we're also running the Nemotron orchestrator 8 billion parameter model to orchestrate the activities between our Python and our SQL agent. So we're running 3 small language models all on my laptop, returning real results in a small amount of time using very little resource. I hope you enjoyed that demo. So why are we talking about all this and highlighting the economics? If you go back to what Jensen Huang said about the best engineers should be using at least $250,000 worth of tokens, and OpenClaw burning $2,200 worth of tokens in over a 12-hour period, here are some articles saying that tokens will be the new oil. We're easily looking at a world where token costs are going to be a significant portion of our tech budgets. It goes without saying, usage is climbing. Both individuals and power users are burning more and more tokens. Agentic solutions, where language models are going to invoke other agents, is only going to cause the cost to climb exponentially. We also know that capital expenditures are skyrocketing. The hyperscalers spent tens of billions of dollars in 2025. And the committed spend in 2026 is now in the magnitude of multiple hundreds of billions of dollars. The amount of money being allocated to build out these AI data centers is massive. If capital expenditures are increasing, where's the profit for these hyperscalers and inference providers? All inference providers are going to need to do something in order to justify the cost of the spend for these data centers. The big question is, when the price does increase, what are you going to do about it? If you remember, Anthropic did a test to see how palatable it would be to remove access to Claude Code from the Pro subscription amid outages that were happening at the time. After a huge outcry, Anthropic quickly added the functionality back. A ton of people were joking around on Reddit claiming, well, it looks like I can't code until Claude comes back online. I hope that isn't your answer when costs potentially make access unattainable. There are a lot of people saying if you purely look at the math and the replacement hardware costs on how quickly GPUs are advancing, it's not sustainable to replace the GPU infrastructure every 3 to 5 years. What's the driver of that statement? Well, if you look at the performance increase between the H100s, the H200 platform, and now Rubin Vera, each generation is making such significant performance increases and improvements, it's obsoleting the prior generations. And I'll leave you with this. Don't take my word for it. The NVIDIA research paper is literally declaring small language models are the future of agentic AI, and NVIDIA invested $20 billion for licensing costs on Grok's TPU technology to integrate that into the platform to drive down the cost of inference. Google recently announced their TurboQuant platform, which significantly decreases the amount of memory needed by simplifying vector geometry, which allows for higher quality quantization. This caused memory chip stocks to drop significantly. It seems like the big players and leaders are investing in it. The call to action is, so should you. So for resources for this presentation on small language models, fine-tuning, quantization in the scope of agentic AI, all the materials, including the slide, the code for the demos, are all available on my GitHub at that link. If you're interested in hearing more about inference costs playing a part in how your AI solution makes it to production, I would invite you to take a listen to a podcast I recorded with ODSC, and I also wrote a blog post to support the episode. I hope you found the presentation interesting and informative. Thank you for listening.